One kind of job you might have as a drafter or a designer that's kind of interesting is starting with a formed view and developing a flat pattern from that view. If you have something that is cubical or rectangular, a cube or a rectangle has 6 sides. So you're picturing what are the 6 sides and what do they look like when they're stretched out. If you have a cylindrical shape, then the long rolled out part is the circumference of that cylinder, and then you have 2 round ends on it. You might do a rolled out shape if you were doing some sheet metal duct work. If you have a prism or a thing that's tapered, you have some combination of triangles and trapezoids, and this too is a common shape in tapered connectors in sheet metal ductwork. This kind of flat pattern stuff is used in packaging design, and this is a whole specialized field. In fact, there's a packaging engineering magazine that you can subscribe to. Sheet metal designers use a lot of flat patterns. This is probably the place where you'll use this the most. And you'll notice here's a flat pattern for this part. Here's what the part looks like when it's formed. And notice that there are bend lines. This bend line has been bent up towards you. This bend line has been bent down away from you. And this is the machine that does the bending. This is called a press brake. This particular press brake is in the welding and fabrication shop at LCC. And for plate, it looks like this. I say that there's a thing called a finger brake that you might use for thin sheet metal, but this is what we use for thicker sheet metal and plate. So there's a pair of dies. You can see the end view of the dies there. There's a V-shaped opening and a V-shaped nose that comes down in there. And you put the piece of plate in between those 2 dies, and then you step on a pedal and it brings the top die down into the bottom die, and that piece of plate that was flat gets pushed down into that V, and here you can see in the photograph it forms an angle, usually 90 degrees, although we can do different angles. Now think about how that die comes down into that die opening. The nose of that die gives you a bend radius inside the metal, and how sharp that corner is determined by what size the radius is on the nose of that die. So if you want a sharp corner, you'll have a die with a small radius. If you want a big corner, you'll have a die with a large radius. And there are limits on how small we can get before the metal on the outside of the bend starts cracking and you get what you call orange peel. As the metal bends, it changes length. And think about, what if this were not a piece of metal but maybe a big kitchen sponge or a big sheet of foam? And as you bend it, you can see the bubbles in the sponge or the foam are getting stretched around the outside of that bend. And they're also getting compressed, squished together on the inside of the bend. And somewhere in between those 2 extremes, there's a place where it doesn't change length. But the net effect is there's more stretching than there is compressing, and so the metal actually gets a little bit longer when you bend it. And we figure that out with something called bend allowance, which we'll look at next time. Now, if you calculate what the bend allowance is for different pieces of metal, you will discover that, yeah, they all stretch out a little bit, but at thicknesses of metal at 3/16 or thinner, the amount of stretch is so small that we can neglect it, that the stretch is negligible. So even though, yes, the metal here does stretch a little bit, it's such a small amount of stretch that we can just act as if there's no stretch because it's a small number. So when you're trying to figure out what your flat pattern will look like, what you are looking for is the inside dimensions. And on this drawing here, you see these dimensions are given to the insides of this piece of metal. And to figure out what numbers do you put on your drawing, you just use those inside dimensions. So on this piece, the first dimension is to the inside, it's 2 inches. So on our drawing, we write 2 inches. And also notice on our drawing, we use phantom lines for the bend lines. They're imaginary, they don't really exist, but they are places that we want our sheet metal worker to mark with their pencil, and they'll put that in the press brake. So we mark those lines with phantom lines, and then we indicate with a note that this is a bend line. Here is whether we want bend up or bend down. Here's how many degrees the angle should be. Even if it's 90 degrees, we tell them that. And then we tell them what bend radius to use. Here's the second dimension. We're also given the inside dimension there, 3.5. So here's the 3.5 dimension from that line to that line on our drawing. What if you only have the outside dimensions? Well, you have the outside dimensions and you know how thick your material is. So what you do is you work from there and find what are the inside dimensions and put those on your drawing. So for example, 3 inches outside minus 1/8 of an inch material thickness takes us to 2 7/8 inside. So there's our first dimension. It's 2 7/8. What if you have some outside dimensions and some inside dimensions? This is very common too. That's no problem. You convert all the dimensions to inside dimensions, and then you put them in your drawing. So here's an outside dimension, the 2-inch dimension. That's outside. We want to get to the inside bend line, so we say 2 inches minus 1/8 gives us 1 7/8. By the way, oh yeah, and let me say one more thing and then I'm do it by the way. So here's another outside dimension, 1.5. We want to get to the inside, so 1.5 minus 1 1/8 gives us 1 3/8. That will be this final bend here. Now the middle bend is 4 inches and they give us the inside dimension there. Oops, they give us the inside dimension, so that 4-inch dimension we can just keep because that's already inside. What I wanted to say as an aside is there's not such a thing as sheet metal that is 1/8 of an inch thick. I just put this as an imaginary theoretical thickness here so we could be thinking about sizes. There is a sheet metal 10 gauge is 0.135, so that's pretty close to 1/8, but there's not a sheet metal gauge that is 0.125. Just want to say that. Moving on. What if you want to do a circular shape? Now this is not that common. There are some large diameter round things where you get specialized metal shops that can form them, but you might have a part of a round thing. Anyway, remembering that the bending happens on the inside of this part, you just calculate the inside circumference. And what is the formula for circumference? Thinking back to math class, circumference is 2 pi r. Don't get this confused with area. So area has a squared in it. Area is pi r squared. We don't want that. We want the one without the squared thing. It's not an area, it's a circumference. 2 pi r. Or since 2 times the radius is the same as diameter, you could also just write pi times the diameter. Now thinking about radius and diameter and going from outside to inside makes us want to stop and make a sketch for ourselves so we can figure this out. Going from outside radius to inside radius, we just subtract the thickness. If we're doing a diameter, remember that we have a thickness on each side of the thing. So we go from outside diameter minus 2 times the thickness to get to the inside diameter. And again, we'll just keep repeating this. You want to get to the inside. If you have the outside, get to the inside. You often wind up making sketches for yourself, so here you could do the circumference of half a circle. There it is, half a circle, and then add the straight stuff, 6 inches and 6 inches. If you have just the outside, subtract the thickness so you can get to the inside, find the circumference, there's half a circle, straight stuff and straight stuff. You can do the same thing with a quarter circle, a quarter of the circumference, straight stuff plus straight stuff, and so on and so forth. Let's look at our assignment, our quiz that we're going to do. Now for this first quiz about bend allowance, we're going to pretend that metal doesn't stretch, just so we can begin thinking about how to find the inside bends of these things. So in this quiz, we're going to look at a bracket with sharp corners, and we'll pretend the metal doesn't stretch. And here at the bottom are 2 different versions of dimensioning the flat pattern, one with chain dimensioning and one with baseline dimensioning for the same part. That would be a better method, of course. So the key to filling in these dimensions is that we want to find the inside lengths. Here we are, this first length, we want to go from the outside of the leg to that inside bend. What do we know? We have in the formed view 10 inches overall, then we have 6 inches inside that. The balance, 10 minus 6, leaves 4 inches left over, and that 4 inches is divided between the left side and the right side. So it must be that the left side, this inside length, must be 2 inches. Let me jump down to the bottom of the slide here, because this dimension number 3 is a little bit more straightforward. 1 and 3 are straightforward. In number 3, we are given the outside width of 6 inches, and we are told that the material is 3/8 of an inch thick. So 6 inches minus 3/8 minus 3/8, we must have what? 5 1/4. Looking at inside dimension 2, this is maybe a trickier one. 2 and 4 are the same situation. To find, and what we're thinking about here, let me just back up to our flat pattern. We're thinking about when this plate is stretched out flat, where do you mark the bend lines on this flat pattern? So now, dimension 2 and 4. To mark the lines on the flat pattern, you need to think about the inside bend, the very first inside bend, it's right here. And the second inside bend is inside up here. So this thing here is the length between bend 1 and bend 2. And what do we have? 3 inches minus 3/8 minus 3/8. So we must have 2 1/4 there. And we have the same thing for dimension 4. And then dimension 5 is identical to dimension 1. We're doing the same thing with this bracket. It's not symmetrical this time, but again we're looking for inside dimensions, and here I've marked for you how to think about those.